thanks you all for the introduction. And actually, you all set the task harder for me by saying this is connections to things I don't know if it's connected to in the morning. Yeah, okay. But so this joint work with my brother Manoj Prabhakaran and his student Varun Naran at TIFR. So zero communication reductions. So let me just go ahead and define what this thing is. So ZCR stands for zero communication reduction, and there are two parameters here. There are three things here. So let me just describe what these things are. So psi is some. So there are Alice and Bob, first of all, very prominently, and there is a correlation they are getting from the sky. So calling it psi. They get some inputs x and y. And their goal is to compute some function of x and y, and could be symmetric, need not be. So I'm saying Alice gets output A, Bob gets output B. What can they do to do this? It seems like they're not allowed to communicate. So that's a zero communication deal. So what can they do, hope to do in this case? So we're giving them a little more help. They get access to a predicate, phi, and they can send their inputs, some inputs, u and v, to this predicate, and the predicate says yes or no. And the requirement is the following. If the predicate says yes, then what you should compute should be the correct answer. And if the predicate says no, no correctness guarantees, you just discard A and B. And of course, you want some non-triviality. So the predicate should say yes with some probability. Okay, and that is this mu. So I'm going to use the logarithmic scale. That seems to work better. So the probability that the predicate accepts is at least 2 to the minus mu. Okay, so if mu equal to 0, then it has to accept always. If mu is finite, it's rejecting with some, it's accepting with some probability and rejecting with the rest. So that is CZR.
What is the definition of that again?
It's a predicate. It's not a number. It's a 0, 1 bit, right? So yeah, it just says delta equal to the output of phi on UV is, I'm just calling it delta. Maybe I shouldn't have written delta. It's phi of UV. Okay. Okay, good. So this definition doesn't have any privacy. By the way, before I get to the privacy part, there is a notion of zero communication protocols, and I saw it first in a paper by Kerindis et al., and they attributed to a paper by, some work in the quantum information community by Gizen and Gizen. This is in the context of Bell inequalities, and where there are aborts involved and so forth. But for us, we are going to go ahead and also include some security conditions. There are two versions of this I'm going to tell you. The first one is a weakly secure ZCR. So in the weakly secure version, you think of there being an adversary who just sees this predicate's outcome, whether it is accepted or not, and it should learn nothing. So the predicate, the probability with which it turns 1 should be independent of xy. Okay, so that is a weak security. Does that make sense? And the stronger notion of security is more along the lines of secure computation. So imagine Alice is corrupt. So what all does she see? She sees XR, U, A, and we are still allowing her to see the delta. The adversary sees the delta also. And all of that should reveal nothing to her beyond what she's allowed to learn, namely x and f of xy. Okay, so she's allowed to learn f of xy. And similarly for Bob. Okay, so that is the secure ZCR. Yeah.
So delta seems to be always 1, then or mu is a parameter, it may not be.
Mu is a parameter. If you can get delta always equal to 1, that's the best case you can hope for. You may not be able to do that, right? You can write this in notation. So this is what it is. Doesn't matter. Since SZCR is too complicated, and since we are in Italy, I'm just going to call it Scissor. Okay, and this is a secure Scissor because Scissor comes with a lot of security. The weakly secure, weak Scissor looks like this. Okay, so weakly secure zero communication reduction. Okay, so I'm going to use this too. So I will be talking about all three notions: ZCR, Scissor, and weak Scissor. And I'll try to distinguish them with these pictures when I can. Okay, so this is a completely new primitive. It's unpublished work, hopefully not unpublishable work. But we are still working on it. We don't know. There are some lower bounds somewhere in there. Yeah, it's mainly lower bound. That is the motivation. Okay.
Can you motivate this data?
Okay, so mainly without this predicate, there is very little you can do, right? How are they going to get the correct answer if they do not communicate at all? It's a non-signaling kind of situation. So you cannot hope to do anything, right? There is something I'll get to at the very end where you can hope to do something without this predicate being around. So we are allowing this predicate to, so they are saying, I'm going to put my output out there already. And then this referee comes in and decides whether to accept the output or not. Okay? And they don't get a second chance. However, the definition does allow amplification if you want to, in the sense that you can repeat this several times and it'll still stay secure because the probability of accepting doesn't depend on X, Y, and so forth. So you could think of repeating it, but for now, this is the definition.
What is the probability of delta equal to 1 over? Is it for random U and B, or is it for run of the protocol?
It's random RS and the randomness of these guys. XY is fixed, so for every XY. Okay, so since this is a new thing, you just spend some time on it and you see a lot of simple things you can talk about. But the quantities of interest would be mu, the acceptance probability, or so mu is 0 means very good and mu is infinity means very bad. And what are these phi and psi that so it's a reduction. We call it a reduction because you are reducing it to this predicate. You didn't fully solve the problem, right? You just put out this A and B, and now it remains to compute phi of UV to say yes or no. So it's a reduction to phi, and it is with the help of psi. So you get access to psi. And ideally, the psi should be something very simple, just a common random string. And this phi also ideally should be very simple, like just an AND predicate, which was the case in the initial work kind of mentioned Kennedys et al. So what can we say? So for every function, you can give a weak Scissor, which actually does this. The predicate is just and the correlation is just common random string. Okay? And it's very simple. Actually, it's trivial. All you do is, in the common random string, there will be a candidate X and Y. And you just send to the predicate whether your X matches that one, and the other party sends whether their Y matches that one, and they compute f of x and put out the output. Right? What is the probability of accepting? It's if the what is in the sky matches what we are given. Okay, so 1 over x.
Why do we need the randomness in the sky? Can't I just guess the input of the other party and the predicate checks if they guess is that correct?
No, then I have to say, so then it's not AND, right? So, okay, I have to send my x, it's an equality kind of thing. You could do that too.
Okay.
So since I said we can do it with AND,
Oh,
no.
okay.
Okay, you could do that too. So that is weak Scissor. Unfortunately, when you want full-fledged security Scissor, it doesn't seem like, or we'll see, you cannot quite do it with this kind of simple phi and psi. Okay. So here is one thing you could do. You would say, okay, actually the predicate will, both Alice and Bob will send inputs and candidate outputs and their output to the predicate, and the predicate checks if the output they picked is correct. Okay, so Alice and Bob just pick outputs uniformly at random, send it along with their inputs, and the predicate checks if AB equal to X. And then the probability of hitting it right is just the output domain size, right? 1 over the output domain size is the probability. You could flip things around. You could say, I want my predicate to be really simple. My predicate is just going to be and instead I'll offload the work to the correlation I'm given. So in this case, what the correlation puts out, random XY and random AB, and then both parties just check if the X and Y are compatible with their respective inputs and send that to the AND predicate. Okay? So in this case, the acceptance probability is 1 over the input domain.
This sounded the same to me as what you said in the first.
Yeah, so in the first one, they didn't have anything in the sky. Right? There was not even a CRS needed. They just guessed.
The first bullet sounded the same to me.
This two?
Yeah, the first
and first and the third. No, here there was no computation. Here the correlation computed candidate inputs and outputs. Okay. So actually, good question. Why is this not a weak Caesar? Why is this not a Caesar? Only a weak Caesar. So you learn the other party's x, right? If you know that acceptance is, it's going to accept if what is in the sky is the other party's input. So the acceptance tell you the other party's input. Whereas not just the output, right? It tells you the other party's input itself. Whereas here you only learn if the other party's, the output you produce matches the other party's input and not the other one. So yeah, so this is a secure one, this is a weakly secure one. Okay. Just a couple more basic results. So why not do the Caesar with CRS and AND? Well, you cannot do it unless the function is simple. Okay? And what do I mean by simple? There's a technical definition from some time back. There are many ways to say what a simple function is, but think of it as if the inputs are also picked randomly. So inputs are picked randomly, and if it's a randomized function, the outputs are sampled correctly. That whole functionality is something which you could securely implement. So there is some common information, and conditioned on common information, your views are independent of each other. Okay, that's a simple. So simple function is one for which this randomized function is trivial to securely compute. Does that make sense? Okay, so it's a, particularly simple kind of functions. Those are the only ones for which you can do Caesar with AND and CRS. Okay, the AND as a predicate and just CRS as the correlation. And what if the predicate was XOR? Then what you need to compute also needs to be like XOR. Okay, so these are things you can show. I'm not going into how to show them. It's very easy. Finally, one more thing you could do is, what if you are computing, you don't have inputs. It's just a correlation you're trying to sample. F itself is a correlation. And, but what you're given, the psi may not be the right correlation Fs, right? If it is, then you can just output it as it is. Otherwise, you have to shave off some probability. You have to shave off some mass so that you can shape psi into phi. And what is the best you can do there depends on whether this F is a product distribution or not. Okay, and the further F is from a product distribution, the more you have to shave off, the more mass you have to shave off. So there's something you can do there. But let me move on to kind of more interesting things. So what the whole motivation of doing this was the same like you saw in the Prashant's talk and maybe Amos's talk. All these primitives are very similar to each other. They're all related to each other. This you could think of as just another primitive which is also similar to these things and related to these things. So, I don't know if this is more fundamental than the others or not, or which one is better, but here is something which connects to various things. And I just wanted to show you some of those connections. So the connections are with the connections we have seen so far, we have looked at so far, are with these things. So OT complexity, OT stands for oblivious transfer, is that we know that information theoretically you can compute any functions, any two-party function securely given enough number of OTs. And the OT complexity is how many OTs do you need? Okay, and Amos and Tal had explicitly asked this question a long time back. We still don't have any good techniques. We think it has to be exponential for most functions. We don't have any techniques for showing superlinear lower bounds. So that is a lower bound question, right? How to show lower bounds for OT complexity. Another thing is what's also called the FKN protocol. So Feige-Killian now introduced this notion of a very minimal secure computation model. And Yuval and L kind of refined it, and they have gave the name private simultaneous message. So I'm using it, but in the sense that FKN originally defined it. And so what is the goal here? Alice and Bob, two parties, they don't talk to each other like in this setting, and they are given some common randomness, and they get their inputs x, y, but they don't need to produce the output. They want to make some party Carol produce the output. So in some sense, Carol is Carol gets communication from both Alice and Bob. And the non-triviality is that it should be secure. Carol should learn only f of x, y, and not anything more about x and y. Okay? And we know it's possible to do every function, and the question is, what's the amount of communication or the randomness needed? You want to minimize those things. Okay, so that is PSM, private simultaneous messages model. And then what Prashant talked about, CDS. So Alice and Bob are given x and y, and there is also a secret which I just said Alice gets. And they want to communicate the secret or disclose the secret to Carol if f of x y equal to 1. Carol already knows x and y, so no secrecy about x and y, it's just this s that should remain secret. Okay? So these are the three things I'm trying to connect to, and the connections we have are roughly like this. So the full-fledged Scissor, we show claim it a path. We really don't know if it will work out or not, right? But it seems like a new way you could try to show OT complexity low bounds. Of course, that would require you to show some low bounds here, and we have no clue how to do that. Weak Scissor, we connect to private simultaneous message protocol. We actually give an upper bound, so sorry, but it's a very simple upper bound, but it seems like a new way to look at the problem. And finally, the ZCR itself has some easy connection to CDS. So let me maybe I'll start off with that, and then I'll tell you the other things.
Because we know that, say, well-behaved PIR protocol locally implies low OT complexity, so are you saying that strong
For OT complexity?
Yeah, we know that if there are good locally decodable codes or PIRs, then the OT complexity of every function is low. So what would this mean for CDS?
So I would be conjecturing that all of these low bounds are high. In particular,
The question is whether there is a barrier showing that
yes, in fact, yeah, yes, all those low barriers will now translate to barriers here also. Yeah, so we are not doing anything. We are just saying here is a new way to look at it. Maybe you can break those barriers or do do something else. But yeah, it's just a connection for now. Oh, okay. So before I go ahead and give those connections, one quick word of some fudge factor we have. So I'll define something called a notion of partial protocol, like partial functions. Basically, this idea of what we had in the ZCR. They don't always produce outputs. They can abort with some probability, right? And oftentimes, I'll just care about being able to produce the output with some constant probability. So when I talk about CDS or PSM, I'll give partial protocols for that. They have now that there is an abort probability, and when there is a security question, you need to ask about how that factors in. It's the same as in the selective abort security for MPC, for instance. Namely, the probability of abort you should be able to simulate just knowing what you're allowed to learn legitimately. And yeah, we could consider a constant probability like half, or in some cases I'll just leave it at a positive probability, non-zero probability, right? So even in a non-zero probability, things are non-trivial because conditioned on the predicate turning out 1, conditioned on not aborting, you need all your security and correctness properties, right? So if you could ask for even perfect security and perfect correctness properties. So asking for a low non-abort probability doesn't make your life necessarily easier, okay? Yeah, so I will use these partial protocols to state these connections, but they can be amplified all the way sometimes to negligible error. Okay, so let me start with the simplest thing. So the connection between ZCR and CDS. So given a ZCR from some function f that you have in mind, so it's a predicate f, to some predicate phi. Okay? I'm going to give you a CDS for f. So this is my ZCR, and they are actually sending this u and v to a predicate phi. Well, and so far there is no secret or anything, right? ZCR doesn't involve any secret string that you want to disclose. How do I use this for building a CDS? So So to build the CDS, I get some secret also, which I keep on the side. I run this ZCR protocol. Whatever UV I get, now I don't have this predicate to help me tell whether UV, phi of UV equal to 1 or not, but instead I will use a CDS. So I'll need a CDS for this new predicate phi. So this is a reduction from F to phi in the CDS world now. And I'll use this predicate to disclose a new random string. And I'll mask the original random string with this new random string and send it here. Why didn't I send the original, not random, I should say secret string. Why didn't I send the original secret string itself here? Because this predicate may evaluate to 1 even if f is evaluating to 0. Because f of xy equal to 0 is valid. So ZCR will say, oh, this predicate evaluates to 1. But if it evaluates to 0, you don't want to disclose s. Okay, so that's why it's kind of secret shit. So it's a very direct, very simple translation. But what I want to kind of spend some time on is a connection with PSM, or private simultaneous message. So I want to build, first I'll show you, how to get a PSM, how to get a PSM for F from a weakly secure. So earlier I didn't want any, in the previous connection with CDS, I didn't care about any security. It was just a ZCR. Now I need a weakly secure ZCR, or weak Scissor, from F to phi. And again, it's going to be like a reduction. I'll need a PSM for this new predicate, which I'll describe. Okay, so this G phi is basically this. It takes 2 inputs, UV, but along with 2 random strings. And if phi of u equal to 1, it will disclose those random strings. Okay? It might look like a complex thing, but actually it's very simple. If, say, phi is something like and, you will have a very efficient protocol for this. Okay, so what does a new PSM or PSM look like? Again, it's very simple. So it doesn't look particularly deep. So basically, they just run the weak Scissor along with some random pairs R1, R2, which are used to mask their outputs. Okay? And so why is this secure? What is this getting as? Oh, by the way, and the predicate itself is implemented using a PSM for this G phi. Okay? So of course, if the PSM protocol says yes, UV equal to 1, then you get R1, R2 out here, and you can recover A and B. Okay? And that's how you'll compute. What do we need for security? So first of all, this PSM protocol shouldn't reveal anything about UV, right? So that is okay. It doesn't reveal anything other than the output, which is R1, R2. But more importantly, even when predicate of UV is false, this guy learns that the predicate turned out to be false, right? So you learn the event of predicate accepting or not, and that shouldn't reveal anything about xy other than the answer possibly. So that's why we require weak security there for the ZSER, right? So we say that we require that the predicate being 0 doesn't reveal anything about UV. That event doesn't depend on, of xy. That's so this works out as a PSM protocol. Now you might think, okay, this doesn't look like a particularly interesting thing. Maybe it's not, but here is some interesting version of it, or we thought interesting translation of what this gives us. Okay, so here this, so you can forget all this ZSER and everything for a second. This is in terms of monochromatic tiles. So for any function, two-party function, you can think of a tiling. There are better tilings, worse tilings. The only requirement is that each subset here, a tile here is a rectangle, and it's monochromatic. So f of xy is the same value in the entire tile. So from this tiling, I will give you a PSM protocol. I don't know, maybe it's a folklore or people already know, but it seemed new to us. So here is the common randomness. It's take any tiling, it's fixed. The common randomness gives you a random permutation of the tiles. And for each tile, there's a color, right? That color is secret shared between Alice and Bob. So a random pad for masking that tile. Also a few bits that we'll need to do a PSM protocol for a single bit of AND. Okay, so that's all in the common randomness. And here is a protocol. So for each tile, which is a rectangle x cross y, Alice and Bob do in that order in which they are kept in the common randomness. So Alice checks if her input is in the tile, is in the X range of the tile, and that's her bit to the AND protocol and predicate. And similarly, Bob. Okay, so Alice and Bob will run a PSM protocol to do this AND. And note that there's only one tile on which this AND turns out to be 1. Everywhere else, the AND will come out 0. Of course, Alice and Bob don't know ahead of time which one is going to turn out to be 0 or to be 1. So for each one, Alice also sends her share of the color if her input is 1. And if her AND input to the AND predicate is 1. And otherwise, she sends a random share. Okay? So from the point of view of Carol, the third party, there will be one tile for which the PSM protocol comes out 1. And at that time, if you put the shares, you'll get the color, the correct color. And everywhere else, you just get a random color. Okay? So this is a PSM protocol. It doesn't necessarily do very well than, there are much better protocols in the worst case for things like the Ishii-Kushler commutation and so forth. They do much better in the worst case. But there could be functions, or there are functions for which this could be better. Okay. So why? But okay. So I kind of jump to this thing without telling you anything about where does this come from our weak Caesar. So the connection to weak Caesar is that actually weak Caesar is doing a little better than just using a tiling. It uses something called a partition. What is a partition? Partition is a fractional notion of a tiling. So you have a weight, not a distribution, but weights assigned to tiles, such that every point xy is covered by tiles whose weight adds up to 1. So these are monochromatic tiles, so they have the same color as xy. And the goal would be to minimize the total weight of all tiles together. Okay, so it's a bunch of, you put weights on all possible monochromatic tiles, such that every xy is covered by weight 1 of tiles, and your goal is to put as little total weight as possible. Okay, so this thing was, well, I'll give the reference in a second. What turns out is that this thing is exactly, it translates to a weakly secure or weak Caesar to the AND predicate. Okay? And what do I mean by exactly? It's a two-way connection. So the best about probability you can get, which is the maximum 2 to the log minus about accept probability, is the same as this partition number, which is the best thing you can get here. Okay? And this thing, so this thing was defined by Jane and Clark in the context of communication complexity lower bounds. They called it partition bound because it's a lower bound. I'm going to call it partition complexity because I think it has a meaning of its own. And in fact, in a previous work, we showed a connection between, or we showed that this thing is actually the same as something called, which we define, called Rene information complexity of pseudo transcripts. I'm not going to define what that is, but it's a information theory quantity you can define. So now what we are saying is that, yeah, so this was already known, and we are just showing that this weak Caesar is exactly the same thing. It's just a tiling. And Jane and Clark actually defined a notion which allows some error, and that connection, this connection goes through for that error also. For us, if you allow the error, that error here only corresponds to correctness error, not security error. A better notion, if you want to work with statistical weak Caesar, is what is defined by Kerendis et al. Called relaxed partition bound. Okay, and yeah, then this connection goes through there with some appropriate translation of the error parameters. Okay, so what I showed in the previous slide was, so this is still a partial a PSM protocol that you get. So you take this W Caesar and use the thing connection from 2 slides back. You get a partial weak Caesar where the, okay, I think I should just go ahead because I'm running short on time. yeah, at the end of the day, what does it all translate to is this. So we can remove this partial and by repeating, but you'll still end up with a negligible error. So let me call that statistical PSM. And the statistical PSM complexity for every function we can now say lies in this range, where the connection with information complexity, something called internal information complexity that I'm mentioning here, comes from the work of Keradis et al. And so it's probably different from the other connections we know. We know better upper bounds for the worst case functions, but here, even for easy functions, we can kind of put the PSM within an exponential range, but it's still something, I think is new. Okay, so in the last couple of minutes I have connection between OT complexity and Scissor. So our main construction here is that you give me a protocol, a two-party computation protocol using a few OTs, I can translate into a Scissor with good parameters, namely small mu, so good acceptance probability, and this phi will have low complexity. And the idea is the following. If it's a protocol, there is this nice factorization property. So probability of error transcript conditioned on the inputs and the CRS, the correlation, factorizes as follows, where this is a quantity that solely depends on Alice's side. So the transcript and Alice's input and Alice's side of the correlation, and this from Bob's side. Okay? And so the high-level idea is that let's fix this Q for now, okay, somehow, or maybe we'll sample this Q. And Alice and Bob will sample R and S proportionate with probability proportional to this rho and sigma, so that the probability of getting the whole thing together is proportional to the product. But of course, not all R and S are going to be good because they were sampled independently. They don't necessarily satisfy the correlation, and that is all that this predicate checks. If the R and S are in the support of the correlation. And this almost works. There are a bunch of technicalities because, in particular, it's not even weak CCR, what I just now described. So you need to adjust your probabilities appropriately. And it turns out you could do all that and not suffer a lot in terms of acceptance probability. So you can end up with a mu, so negative log acceptance probability, which is n plus m, where n is the input size, and m is the number of OTs that are used in the original protocol. Okay? So that is the connection, the lower bound connection. So if I give you a lower bound of t on this mu, or on the complexity of this phi, right, then that translates to a lower bound on OT complexity of f. How good is that? Like, can you expect that it's fairly tight? We don't know. But here is some kind of argument along those lines. So can you go in the other direction, right? Given a good Scissor, can you get a low OT complexity? We can't quite get a low OT complexity. What we can get is a partial OT complexity, where we are going to just accept with some positive probability. Don't care about accepting with 1 minus negligible probability. And then you can show that this partial OT complexity is at most the OT complexity of this predicate phi. Why? Just implement phi using a two-party computation protocol. That's your final two-party, that gives you a protocol. Now, but maybe this partial OT complexity is no good. It's a very small number. Well, we are going to conjecture that actually no, it's also probably as so there is already kind of a conjecture. I don't know if it's formally stated anywhere or it's an open problem, that most two-party functions have exponential OT complexity. I would conjecture, or we would conjecture that the same thing holds for partial OT complexity, even if you only need to accept with a small probability, negligible probability. And a bolder conjecture will be these two things are close to each other. So in that case, this connection is fairly tight. Okay, last one thing I have is the version where it's a zero Scissor, which means there is no abort probability, accepts with probability 1, in which case the predicate is useless. And in this case, the only thing you can do is sample inputs with sample outputs without any inputs involved. And in that case, you can write a linear algebraic characterization of what a secure protocol is. You can use some, kind of Perron-Frobenius kind of arguments. And you can show that basically local randomness and common information and so forth are not useful. And then you can use it to get some positive, and I mean, in one case we can characterize what all you can do with this kind of things, but there are, of course, many open problems. I think I'll stop there.
Okay.
Yeah, thanks.